Hi everyone, and welcome to the first online event from FunctionalFest. Before leaving the stage to the speaker of today, which is Giovanni Gonzaga, I'd like to present a bit who we are and what we do. So we are FunctionalFest, just a group of Italian developers in love with functional programming. Everything started when some of us decided we wanted to do a conference on functional programming in Italy. And so we started gathering a bit of people who would like to help doing that. And nowadays it's something like 10 of us. We wanted to organize a conference. We started programming to do it on June 2020. And then COVID came. And so first we decided to move it back to November 2020. And then we decided to go online. And so here we are, basically. And the idea we had is just to gather all the different souls and community which gravitate around functional programming, both in Italy and abroad. And so we organized a series of 4 talks, basically one per month in the fall 2020. So the one of today is our first talk, and next month we will host Matthias Verais, who is a prominent figure in the DDD community and a functional programming lover, who will speak us about parser combinators. So if you want to keep in touch with us and follow what we do and the events we will come in the forthcoming months, you can follow FunctionalFest on Twitter. You can subscribe to the YouTube channel you're looking right now. And you can also register to our newsletter on our website, www.functionalfest.it. So let's come to the reason why we are here this evening. So we're here to listen to our first speaker, who is Giovanni Gonzaga. He's a technical lead at Buildo, and he will speak about TypeScript and functional programming and introduction. Just one, say, technical note. If you have questions, please ask them in the YouTube chat. At the end of the talk, we will ask the question to the speaker and he will answer as many of them as possible. So with this, I wish you a happy talk and I leave the stage to Giovanni.
Okay, thank you, Marco, and hi, everyone. I guess it's a good time to also share my screen now. Okay, you should see it now. So, well, tonight we're going to have a very, let's say, beginner-oriented introduction to functional programming and functional programming in TypeScript. So in my day-to-day job, it's actually when I manage to be able to actually write code and not do something else, I usually write code in TypeScript and yeah, using also the FPTS library, which I'm going to show you in a bit. I hope for this talk to be very, easy to understand. I'll try not to use complex terms. Also, I do not consider myself, let's say, an expert on the functional programming topic in general. So feel free to ask any questions, as Marco was saying, but also to provide corrections or clarification. We can discuss them at the end. I will not probably look at the questions live on the YouTube channel, maybe just from time to time, but at the end of the talk, we'll have some time to answer those. Okay, so I would say let's start. This is the classical intro to FP that you're probably already used to from other talks or online blog posts, I don't know. So what people usually saying is the paradigm shift from object-oriented programming to functional programming is actually a very simple one, because every complex topic that is characterizing object-oriented programming in functional programming in FP is only just functions. So it is true, this is true in some sense, but also it is not a complete picture, because yes, in the end, everything is just data and function where we're talking about FP, but the reality is that you need to be familiar with many new topics and concepts, and possibly also complex ones. So when you actually start to let's say, work or try to understand the FP in a library or in a new language, you're faced with many new, possibly complex terms like higher-handed types, algebraic data types, or monoid or functor. I'm not even going to mention the M word, but you get the idea. It's not that easy as someone is saying. And this is also true for TypeScript and for FTTS. So if you're doing or trying to do some functional programming in TypeScript, the way to go is using the FPTS library, which is sort of the standard in the community to do FP. But also as part of FPTS, FPTS as a library comes with many topics that should be, okay and familiar for everyone already familiar with FP from maybe other languages or other libraries, but require a lot of learning upfront, at least for the theory part, let's say. For tonight, what I want to actually present you is a few very simple things. We are not going to go into, let's say, theoretical details of any sort. Let me actually move this to the other screen, which is better. Okay. So we'll see what I consider to be some of the rules to respect or abide to in order to actually be able to do some typed functional programming in TypeScript, and we'll see in a bit what I mean by this. I quickly present some functions or helpers or features from FPTS. We'll see also more along the way with more examples. And I also try to explain what I mean about with type-driven design. We see also some examples in terms of code, and same goes for parsing, the last part at the end. So imagining you probably already had a look at FPTS in the past if you're familiar with TypeScript or the TypeScript ecosystem. Otherwise, if not, this is what you're confronted with the first time that you open the FPTS on page on GitHub, let's say. FPTS is a library created by Giulio Canti. It brings some FP concepts that are popular in other languages like Haskell, PureScript, or Scala. It brings them to TypeScript. It is based on a custom higher-handed type encoding. If you know what they are, it's actually based on the lightweight encoding mechanism, which is a technique which is also used, I think, in other languages like OCaml, or at least in other libraries. And this is necessary because TypeScript does not support higher-handed types at the moment, even though, yeah, just today I read about a new pull request by someone trying to actually add proper support for higher-handed types in TypeScript, but it's not there, and it will not be there for a long time, if it ever will be, let's say. FPTS, contrary to other libraries you might be familiar with from the JavaScript or TypeScript ecosystem, it comes with, let's say, a real or full functional programming concepts. So not just the, I don't know, the point-free programming style that is offered by other libraries, by like Ramda. So it brings in the full package for FP. It has its own quirks, but it's fairly complete. Also, contrary again to other popular alternative in the JS land, at least, it is focused on typed functional programming. So let's try to see how TypeScript can help us, and try to understand what this means in practice. So when talking about FP in a very simplified form, we can assume the following. So in FP, you always consider your object, your values to be just plain values, so no behavior attached. Generally, they should be treated as immutable values, so meaning that different values or an update to a value should also correspond to a different reference. This is I mean, this works if you're using the standard JavaScript quality, at least. There are ways around this. There is a type class for this also, of course, in FPTS. But yeah, let's stick to this in general. And then other than data, you have, of course, functions. Functions in a typed TS world or a typed FP in TS world are to be intended in the mathematical sense. So no impure functions, no side effects in your functional implementation. And also each element of the domain, so the type in input should map to a single element of the code domain, so the return type. And of course, the function should be total, so it should not be partial, actually, speaking in a mathematical sense, so it should be defined for every value of the domain. And well, TS does not a great job in general in helping us, let's say, respecting this, achieving this objective here. But it can do some things. I have a few very basic rules that can help us at least trying to achieve the most out of this, at least what is possible in TypeScript. So first of all, everything that I will say in the following of this talk tonight is based on the fact that you're using a strict set to true in your TS config, so the config for the TypeScript compiler. Without this flag turned on, we are basically speaking about a different language completely. Second rule might seem weird to someone, but I think it's a very good practice to always annotate the function return types. We'll see a specific example later on where this is actually needed, but also I think it's a good idea to do this in general because you'll find it very beneficial, at least in a refactoring phase, so you understand precisely where exactly you should change the function signature, or you should actually go and fix the errors that the compiler is throwing at you at any given time. Also, of course, as we said earlier, always define total function. So the return type that we annotate for the function should actually be a real one, a correct one. We'll see a few examples in a second. We should not try to lie to the compiler in some way, and there are many possible ways that we can lie to the TypeScript compiler. Of course, it does not a great job at preventing us from cheating. Also, this is a bit more far-fetched probably, but after some time, I think you'll understand it when possible. You should always prefer to write functions that are polymorphic. So in TypeScript terms, functions that have generic type parameters. The reason for this is, well, actually very simple. Usually, if you try and manage to actually implement a function on a generic type parameter rather than a concrete type, you can make much less assumptions on the value itself, or what's contained inside of the value, and on the characteristic of the concrete type, let's say. So this in turn means that your function typically becomes more general, reusable, or someone should say probably orthogonal with respect to other functions. And this means in turn that you'll be able to actually reuse in the code base that function much more. And yes, then last but not least, what I wrote here is, well, type-driven development is almost a joke, but anyway, not everybody knows that TypeScript offers this possibility. So basically, the possibility to declare a function without specifying its implementation. This is, I think, a good practice to when you actually have to start to develop a new piece of code, a new feature in your code base, starting from the signatures alone, so without providing any implementation. And we'll do this for basically all of the rest of this talk. So I usually abuse this technique. Starting from the signatures only is better first, because you don't spend time trying to implement something that you don't yet know will work as you wish, as you desire. So when you are then fine with the current signatures, you can probably then start implementing the function for real, and don't spend time doing that multiple times earlier. Okay, just one last bit. As you can see, probably already the rules that I'm listing here are not really related to functional programming. I think they are good rules in general. So I suggest you to follow these rules anyway when you write TypeScript, even if you're not interested in trying going FP, let's say. Okay, but coming to something slightly more practical, not very practical still. Let's see if I'm listing a few functions here. So let's see if these are respecting the rules that we just saw. So the answer is yes. Every one of these should respect the rules. Why? Well, because we annotated the return types. I'm also using a declare function here, but this is not really a rule, it's just a suggestion. So take, for instance, the second one, so length. It is accepting a string and returning a number. I assume it will be implemented as a .length to retrieve the length of a string in JavaScript, which is very possible. It is defined for every possible value in the input, because for any string we can obtain its length by accessing the length property. So yes, it is a total function. It is respecting our rules. Same goes for the other two, actually. Let's see some other examples instead. So the first one is not something that we made up. It's actually a function available in the window or DOM library, let's say, in JavaScript. So it's the parsing function. It is saying, yes, I'm accepting a string and I'm always returning a number, which of course is a big lie. As you probably are already aware of, well, this is possible because number in JavaScript also includes the not a number case. So Parsing will probably, I mean, they were confused, not sure if they should have returned or thrown an error somewhere, or instead returning not a number, decided to return not a number instead, which is fine. But well, usually when I try to parse a number for a string, I don't want not a number back, and of course I want to be aware at the type level if I got an invalid number back. So this is not helpful, because for TypeScript, not a number is really just a number like any other. Similarly, in the second example, which is also a typical example, the function is head. This time it is polymorphic, so it has this type parameter A. It works for any array containing elements of type A, and for any array containing elements of type A, it is able to return an A, which is the first element of the array. Of course, this is not true. This is not possible, because of course, if the array is empty, this is not possible. Let's see some more examples in code. So let me switch to the editor now. Okay, I hope it is big enough for everyone to read. So this is the same add function that I was presenting a few seconds ago. Let's try to actually implement it, just to understand that also TypeScript sometimes doesn't really help us in this regard. So this is the same signature, the one that I just said is a lie. We're actually implementing it as accessing the first element of the as array works as expected. So TypeScript does not complain. Of course, this is not a safe access as of now, because we're not sure that this array actually contains at least one element. Another news, pretty recent news, so the next version of TypeScript will actually include a new compiler flag to prevent this kind of unsafe array accesses, but for the moment this only compiles. A safer version would be this one, so where we explicitly encode in the return type that our function can also return undefined. In case our array is empty, this index access at index 0 will just return undefined. So we're making it explicit also in the function signature. So this is a signature that doesn't lie to the user, let's say, and actually respects the rules that I was saying before. So yeah, here I'm just defining a few other functions. We just saw probably all of them. This one cannot be implemented for real. Let's slightly switch to a different topic. So actually start to talk about FPTS. Okay, so the first thing you're probably going to be faced with when actually trying to use FPTS for the first time is the way you are supposed to compose a function in the FPTS world. So I have an example here, just reusing two of the functions that I defined before. So the function length, which returns the length of a string, and the function double, which replicates 2 times the string foo in this scenario. So this is, let's say, plain normal function composition in plain JavaScript or TypeScript. So the result in the end will be, of course, a number. I'm doubling this foo. I will get foo back, and this length will return me 6, which should be, if I'm not mistaken, the length of doubling foo. In some other languages, like if I'm not wrong, I think Sharp, you have this pipe operator available. There is also various competing proposals to have this in JavaScript as a standard syntax, but it is not available at the moment. The pipe operator works in this way. So from left to right, you're able to actually pipe the string foo inside of the function double, which will be, of course, a unary function, only accepting a single parameter. And then you pipe the result of double inside of the length function, which again is another unary function. So our result 1 in this example would be exactly the same as before. So FPTS wants you to compose functions in this way, like if you were using the pipe operator. The pipe operator is not there yet or I'm not sure if it ever will be, but it's not there at the moment, of course, in TypeScript. So FPTS exports this pipe function, which actually mimics the pipe operator. So instead of having this nice syntax, we have this pipe function call, but it works the same. So you're, in this example, you're basically piping the foo string value inside of double and then inside of length, and we will get back the same result of type number. There's also another way to compose functions in FPTS using another function exported by FPTS, which is flow. Flow does actually the same thing, but composes functions beforehand. So you're able to actually compose 2 or more functions together before actually invoking them. So here you can see that with flow, I'm composing from left to right these 2 functions in a new function called double length, and then only at a later point in time I'm actually using it. This works, but you can have some. You can encounter some issues, especially if you're trying to compose functions that are generic and you're not inside of a proper context where TypeScript will be able to actually infer a concrete type that makes sense for the user. So it's not, it cannot be used always, let's say, because TypeScript is very eager in this regard, and it will try to find a concrete type to substitute that type parameter, let's say, too early in the process. Okay, so this is just a very quick introduction to show you how mainly pipe works, since we'll be reusing this function in the next few examples. I would now switch back to a more concrete and realistic, let's say, example, which is this one. So in this slide, I'm sort of defining our domain model, which will be the base for the next few examples that I plan to do. So let's imagine we are working with a car rental form. It's a very simple one. It's made of 3 different fields. So the email, the payment mode, which can be either at pickup or online, so paying right now, and also the age range of the user. So 3 ranges between 18 and 25, between 25 and 27, and older than 27. Also, we have a few additional rules. So basically, the most important one is that the email is only required if we are going to pay online, so right now. If not, we don't want to ask any email to the user. and also how it should behave, well, at form submit or even live while the user is typing. We should be able to display the total price based on the current user input. So the total price, we will assume is only computed based on these three fields here, which is not realistic, of course, but yeah, it will work for our very contrived examples. Okay, so back to the code. These are actually the same rules. I only copy pasted them here. Let's start by modeling our domain. So defining some basic types for the to represent the our domain, or at least a very small domain as I described it up to now. We have the payment mode. As I was saying, it can be either online or pickup. So this is a simple union of the two possible cases. Similarly, for age range, we have, in this case, instead, three possible cases. Also, we need some sort of type to represent what is the current state of the form at any point in time. So even considering like the beginning of the user input, so when the user didn't yet provide any email or didn't do any selection for the other fields. So the email is a string which can also be undefined. Age range and payment mode have their more specific types. So I can imagine in a form they would be implemented with a radio group or some kind of sort of drop down or select combo box, but they can be undefined as well, because at the beginning the user will not have selected those yet. Okay, now, of course, our API will accept valid payloads for our form when you try to submit the form. So in some way, and also our function to compute the total price is based on valid inputs only, of course. So we should find a way to represent the type of the payload that we can then at some point send to the API when user submits the form, or use to compute the total price for our car rental. So let's start to define the type of the payload. So this is a very simple solution, one that you're probably already familiar with and you saw used elsewhere in similar situations. So I have the two fields, age range and payment mode, which are always required. That cannot be optional in our payload type, let's say. But then I have this email type, again, a string, which stays optional because, in case the payment mode is at pickup, as I said earlier, we are not requesting the user to provide the email. So I have to account for also for this scenario when we don't have an email, let's say, to work with. Okay, so let's test this type. Let's try to define a few possible payloads. So these first two payloads are indeed valid ones. So payment mode, pickup, and age range, one of the three is perfectly valid. Similarly, this one, payment mode is online, so this time I have to provide an email. This one is a valid payload as well. But then already with this third payload that I'm defining here, we see that this type definition has some issues. So for instance, here we are selecting the payment mode pickup, but we are also providing an email, and we don't get any feedback that this field is not necessary in this case. Well, probably not a big issue, but the opposite is actually a big issue, because we are also able to assign to our new type, so confirm rent, we are also able to assign to it a completely invalid value, which is like this one. So where we select the payment mode online, but we don't provide actually any email. So this one is a completely invalid payload. And our type, or at least how we defined it, TypeScript is not helping us in understanding that we are making mistakes around our code base. So what we define here is usually referred to as a product type, meaning that intuitively the number of possible states or values that are representable by this type here is equal to the product of of the possible values that each field can represent in this case. So, well, in this scenario, we have this email field, which is can actually hold, let's say, infinite or too many values to actually count what's the total in here. But then we have age range, which is 3, and payment mode, which is 2, because it can be either online or pickup. So we have 3 times 2, at least 6 combinations for age range and payment mode, and then plus the infinite ones for the email string, plus 1, which is would be the email undefined case. So this is why it's called the product type. And as we saw, it actually has many issues because, yes, we are able to assign to it some payloads of not containing valid values. So in other words, this type here makes it possible to represent in our in the types describing our domain model, also impossible states that should not be possible in our domain. Let's try another representation instead, which is this one. So we define the confirm rent, so the same payload made up of 2 different cases, so the online payment case and the pickup payment. And then we define each one with its own payment mode. So of course, the online payment will be of payment mode online. It will have an age range, and it will also have an email, which is required in this case, because when the payment mode is online, we want to have an email. We'll also have the other case, so the pickup payment with pickup payment mode. And in this case, as you can see, we don't have any email defined. Testing again this type, this new type that we defined here, we can see that, well, it works the same for the first 2 cases, but now hopefully it also works correctly for the critical cases from the first example from the product type. So for instance, if I try to provide an email to the case of payment mode pickup, TypeScript warns me about the fact that I should not provide any email in this case because it is not required. And similarly, also in the other scenario, I'm not able to not pass a valid email when I'm selecting payment mode online, because TypeScript knows that in this case, the email field is required. So it's correctly telling me that the property email is missing in our type, blah, 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 but required in our target type for the assignment, which is in this case online payment. Okay, so our new type can still represent infinite values because we have the string, which is still can hold the infinite values. But as we saw, it is removing by design all of the possible, all of the impossible cases that were actually instead representable by the product type that we defined before. It's usually called this form of type definition is usually called a sum type. Again, intuitively, this time it is called a sum type because it will be able to represent the sum of the possible representable values in the 2 subcases that we have here. So the sum of the number of values that online payment can represent and the number of values that pickup payment can represent. We saw how to encode a sum type in TypeScript, because this is a standard technique, actually, the one that we used. So in TS, it is called a discriminated union. You can also find more information on the official TS handbook. Discriminated union because there is a special field in our type definition, which must be called the same in every possible subcase, which works as discriminator. So TypeScript is actually using, is able to discriminate in which case we are, let's say, each time that we interact with a value of this type based on the value of payment mode. So let's see a feature that TypeScript provides if we encode our types with this practice, so the one of using some types or discriminated unions. A very nice feature is this one. So we're able to actually implement functions in a way that we make sure that they are always total and defined for every possible case. And we don't risk to, let's say, forget to handle possible cases in our domain. So this function render confirmation, I'm assuming I get a payload of type confirm rent in input. I annotate the return type as a string, so I always want to return a string. And in this case, it is important, otherwise the exhaustiveness check from TypeScript will not work. And then I'm switching here on the payment mode. So I'm ending all the two possible cases. In one case, I will actually have the email for the user, so I can say to the user that the payment confirmation was sent to their email. TypeScript knows that if you are in this case of the switch, you can actually access safely this email property, because it is able to refine the fact that if this is true, so if payment mode is online, then inside of this block here, email is defined. The same is not true for the other case. So if we are in the pickup case and I try to access the email field, it is not there, because TypeScript was able to refine that in that scenario we don't have any email defined. Of course, this function is, TypeScript ensures that this function is actually total. So we get an error if we forget to handle a specific case, or similarly, we get an error if we try to handle non-existing cases. So yeah, and this feature is particularly useful in some situations, especially when you are refactoring. So let's say that your confirm rent type changes over time. At some point, you refactor it, you change, you add it, you add more possible cases to it, or you remove some. TypeScript will always be able to exactly tell you all of the cases and all of the function implementations that you actually need to update to make your code compilable again. And you're then, let's say, free to make the explicit choice every time in the refactoring phase of when and how to update each function, because we are annotating the function return type. So again, these return types are really helping in the long run, let's say. Working with some types, you'll find yourself probably writing too many switch statements. So a common thing to do is to define some helper functions to operate on the possible cases of the sum type. So here I'm defining a function which is called fold, and it will receive a rent submit in input. And it also requires us to provide basically what to do in every possible subcase of our sum type. And internally, it's just implemented as the simple switch that you just saw in the previous file. I actually implemented this in a carried form, and also a data last, so receiving the rent submit, the second invocation, let's say. For it to work well with pipe, so it can be composed together with other functions in an FPTS pipe. Actually, the name that I'm using for this function is not an arbitrary one. As you will discover if you try to use FPTS, many different sum types are already available inside of FPTS, and all of the sum types that are defined inside of the library of FPTS data types follow this naming convention. So let's just have a quick look at one of the most common one, which is the option type. Option is a sum type predefined in FPTS. Let's have a look at the definition, which is here. As you can see, it's very similar to what we just defined for our specific scenario. Option can represent, well, the only difference is actually that this one is it is a type parameter, so it's a generic type. It can represent two possible different cases. So the one where you don't have any value, which is called none, and the one where you actually have are holding inside of the option, let's say, a value of type A. Each subcase, as always, is encoded using the same technique that we just saw. So the one of discriminated unions. In this case, the tag is this underscore tag field, and of course, as you can see, only in the case of sum, we actually are holding a value of type A, not in the case of none. So option represent optionality, can help in handling errors, or optionality in control flow in general. Open back the correct file. So just a quick usage example for option. Here I'm piping this value here of type age range of undefined for some reason. piping it from nullable, which is an helper function exported by option, which allows you to from a nullable value, so that one that is either a type A, age range in this case, or undefined or null. It allows us to transform it into an option. So at this step in the pipe, we'll end up with holding an option with some value inside of it if the original age range was actually valued to be an age range, or none if instead it was either undefined or null. So this from nullable is from nullable and to nullable. So the opposite transformation is also a good way of interoperating with non-functional code. So to make the two different words speak well together, let's say. So in this, with this transformation, I'm actually entering the FPTS word inside of an option. And then, as I was saying earlier, option, as any other sum type defined by FPTS, also exports a method, a function called the fold. The fold function simply lets you handle all of the possible cases that are defined for this sum type. In this case, we have two. So the left callback is for the none case. The right callback is for the sum case. So we are just using identity here. So I just wanted to show that this also has a shorter version. If you find this in some examples around the internet, getRes is basically defined specifically for option, or maybe also for a few other data types. And it's basically a fold where the second case is handled by default to return the value which is contained inside of the option. So we don't need to provide the identity if we use get or else. Okay, so we saw some types. We saw that they have advantages over product types, at least. But we also saw that there is a few things to define to be able to use them, let's say, proficiently. So there's some boilerplate, mainly, yeah, that fold function. Luckily, there are a few helper libraries, part, let's say, of the typed FP ecosystem, or even part of the FPTS ecosystem itself, which help you define some, yeah, actually help you define the original sum type. So, and also defining the mesh function without defining each time a fold function by hand. You can reuse this mesh function, which is exported and generic, and it works for every sum type defined using the library. So mesh is the same as our custom fold that we implemented before. One of these libraries is TS-ADT by Paul Gray. You can basically obtain something very similar to what we defined earlier for our confirm rent sum type by using this syntax here. So using the ADT type and defining it like this for every possible case is defined its payload, let's say, its data for the case. And then, yes, I was saying earlier, you can also import this match function directly from the library and use it directly to switch on all of the possible cases of the ADT that you define this way. Another common thing to do when working with some types is also defining a constructor for the specific cases. So here I'm defining basically two constructor functions. These are functions that accept the data that that I need to actually create a value of the correct type, of the correct subcase of our sum type. These are handy because when you actually write a lot of code and you need to return types, values of these types, you don't really want to read or write complex objects every other line of code, let's say. Even these are part of the boilerplate that you have to define to actually be able to exploit some types for real. Luckily, again, using other libraries, I'm using an example here using this library Morphic TS, the ADT subpackage. This one can also provide, other than the ADT definition, also the constructors definition. So it has some runtime call to define your sum type. And then you can actually also reuse the constructors for each specific case without redefining them every time. So this again is another example of the same function implemented, I mean, the same pipe implemented using confirm rent as a sum type defined via the make additive function from IOTS, but the function is the same as what we saw earlier. So we are able to mesh with the generally the exported function from IOTS like we were doing before. Okay, so I would say let's switch back to the slides to do a quick recap of what we saw. So some types in TypeScript are encoded as discriminated unions. In general, they tend to, compared to product types, make impossible states not representable, impossible states in our domain. So they have many advantages, or at least you should know when to use them. TypeScript can provide exhaustiveness checking if you implement some functions in certain ways, as we saw earlier. So actually warn you for any possible mistake that you could do operating on product types by, let's say, forgetting possible cases. And yeah, there's some boilerplate to be able to use them for real, but there are helper libraries which can help to reduce at least the amount of code that you have to write by hand. Okay, so this is probably, let's say, if you have to only remember a single thing from this talk, a single slide, this one is probably the best one to remember, because it looks like a very simple concept, but it also changed my life a lot when I discovered and started to actually use it in my day-to-day job some time back. So yeah, the suggestion here is to being aware of this difference between a sum and the product type, and also try to exploit the ability to reason in these terms while doing type-driven design, or while designing the types for your domain. Okay, so last very quick topic, let's say, hopefully, because we don't have much time left. Evolving again on the same example with our current form example. So we basically up to now only defined the type. Now we have a correct payload type which satisfies us. We know how to represent a valid payload. We know when we will be ready to send it to the API, when we'll be ready to compute the total price based on our form input. Let's try to also do the next step. So basically understanding when the form is valid and when we are ready to actually display the total price to the user. So let's start by defining this function is form valid. It's a function that receives an input the form state, so the one with possibly undefined values where the user is still writing and inputting data in the form, and it returns a Boolean value, basically telling us if the data inserted up to now is already, say, ready to be submitted to the API. So if we can consider it valid or not. Also, let's assume to have this total price function available. So again, it is receiving instead of a form state, so a possibly invalid one, it is receiving a valid payload, so the type that we defined before, so a confirm rent defined as a sum type. As I was showing a few minutes back, it will return a number, so meaning the total price computed for our current selection in the form. Let's try to implement the function to actually render the total price to the user. So it will receive an input a form state, which we don't know yet if valid or not. It should return a string containing the message with the total price to the user, or an error message if the form is not yet ready to compute the total price. Okay, so I'm using this validation function, is form valid. If the form is valid, it means that we know that we can display the total price to the user because we have all of the data available. But to be able to actually create a value of the confirm rent type, as you can see in the implementation here, we are forced to cast here. So this exclamation mark is actually a cast. So we are telling the TS compiler, trust us, we know that in this step here, for sure, this age range will be defined because I just checked it inside of this function above here. So what can we improve? Because of course we don't like the idea to being forced to cast in the implementation of this function. So yeah, there are ways, let's say, to, without changing too much the signature of is form valid, also convince TypeScript that in the block here, in the then block of our if, these two fields are actually there because we validated them. But I want to show you a different way of doing the same, so which is more general, I think. Instead of defining validation function, let's try to define parsing function. So a parsing function compared to our validation function should not only tell us with a simple Boolean flag if things were right or wrong. It should also encode in some form in the return type the valid payload that will be ready to actually operate upon to calculate the total price or to submit to the API. So the key difference from this parse form state function compared to the is valid function from before is that we are actually encoding as part of the return type of this function the parsed type, so the correctly validated type. In this case, I'm using option also to mean, well, it could be that the form is not yet valid. So if not valid, we can just return a none. So the case of the option where we don't have a value to put inside of it. Otherwise, if we are able to validate the form successfully, we can actually return some value containing our valid confirm rent payload. So the implementation is yeah, easy, but probably not very concise. We'll see how to make it shorter in a bit. So I'm checking that the values are as I'm expecting. So if it is the case for the online case, I'm also checking that the email is there. And in this case, I'm able to return an online payment confirm rent payload. Otherwise, just default back to none. Similar for the pickup case, I'm returning a pickup payment value. Otherwise, if the sum of age range or payment mode were not defined at the beginning, I'm just returning none. Okay, so let's try with this new parsing function instead of the previous validation function to re-implement our render total function. So before this was the implementation, we had to understand if the form was valid already, and then inside of the implementation, actually, we were forced to cast. With this new parse form state function, which is a parser instead of a validation function, let's say, we're able to re-implement this render total function without using any cast. So again, here I'm using pipe from FTS. I'm piping our, say, possibly partial form state into our parsing function. If our parsing function is actually returning a success value, so we are able to parse a valid payload from the current form state, then we map it to also obtain the total price. So this transformation step will transform our option of confirm rent into an option of number, because the total price function will receive a confirm rent and return a number. And then at the end, I'm folding to get back to a string, which is what I want to render to the user. So in the case where the form is not yet ready, I'm just telling, of course, to fill out the form completely. Otherwise, I'm able to show the total price for the current selection. So this is much better because we didn't need to do any cast inside of this implementation. The only thing that could probably be a little bit cleaner or shorter is the implementation of the parse form state itself. So very last example in terms of code, in the TS world, there is a very easy way to define this sort of parsing function. It is by using the IOTS library. Again, another library by Giulio Canti, also part of the same FPTS ecosystem, let's say. It's based itself on FPTS internally also. IOTS allows us to define parsers in this API that I'm using, which is actually an experimental API, not the currently stable one. They are called decoders, at least the little bit that I'm using for this case here. So IOTS provides us with this domain-specific language to define our, let's say, decoders, which are not simple types. They are actually runtime values, so they are const. They are not type here. With this decoder at hand, you can see that the syntax is fairly similar to what would be the corresponding syntax to define these types in TS. Of course, I'm using functions instead of using the literal type syntax for TypeScript, of course, but the principles are the same. So for instance, here I'm doing using this union combinator, which is the equivalent of doing plain union in the TypeScript type level land, let's say. With this confirm rent decoder at hand, we can re-implement our parse from state in a, let's say, shorter but also a better looking way, which is by passing our form state through our decoder. Our decoder will either fail with some errors or return us a value of type confirm rent. So the decode function actually returns another some type from the FPTS library, which is called either. It's very similar to option, but unlike option, other than having a right case with let's say the correct value contained inside, it also has a left case, which also tracks the possible different error situation. So it has a one more type parameter to describe what's in the left case, which is the error case in general. So to respect the same signature that I had defined before, after using the decode function, I have to pass it through also this conversion into an option, which basically drops the left case for the either and return us an option. Our render total case is unchanged, and this would also complete, let's say, our code samples. So going back to the slides for the last time, a quick recap of what you just saw, why parsing is better than validating. For doing parsing ETS, here are a few suggestions for just the recap of what we just saw. Using parser, we don't need usually to, let's say, use a cast around our code base, which is a good thing, because every time that we use a cast, we lose some kind of help in the future from the compiler in that part of the code. So we should never really use it. Parser, the main difference with respect to, comparing parsers to validators, the main difference is that parsers actually encode in the return type in some way the valid type of the value that we want to parse, and that if we want to define parsers in a really simple way, we can just reuse a lot of the helpers already defined and exported by the IOTS library. Okay, so this will actually be it for tonight. Everything that I tried to say in the last almost an hour probably is already explained much better in some of these links that I provided at the end of the slides. The slides are also available on my GitHub, which is github.com/jogonza, I guess. I'm Giovanni, I work at Build. As I was saying earlier, when I can, also writing code. We are also hiring, so if you're interested in maybe having a look at what we do, it would be nice to get in contact. I'm also one of the organizers of the Milano TS meetup, which is kind of dormant, or it has been at least in the past few months, but we'll get back sometime. Okay, so I guess now we can switch to the question time. So let me open the chat. Well, if I manage to.
Okay, thanks, Giovanni. I want to remember that if you want to, we have time for some questions. So if you want to ask a question to Giovanni, please use the YouTube chat. Let's wait if there are any questions. Okay, we have a question.
So the pattern of consisting of using the unknown type for data coming from outside plus user-defined type guards should be considered a form of parsing or validation. In my opinion, parsing, if I understood the example right. So if you have a user-defined type guards, so actually function signatures, the types is able to understand that are refining the type that receiving input after using those refinements. So you'll be able to also make TypeScript understand that after applying that refinement, you are operating with the value that you have validated and is conformant to what you were expecting. So yes, you don't need to cast anything afterwards. So they should definitely be considered a form of parsing.
Okay, so let me ask a question myself. So, so in your experience, did you already have consolidated experience in TypeScript before embracing functional programming, or you found it easy to start with functional programming and TypeScript together?
Yes, I already had some experience in TypeScript before starting with functional programming. I would not suggest it as the best language probably to start learning FP concepts, because you also have to, let's say, get rid of a lot of burden and additional concepts that don't make it easy to only understand the functional bits of what you're doing. In your day-to-day learning, let's say. So probably if you're only interested in learning FP and you don't know yet TypeScript, it's probably better to use other languages for this objective. So maybe something more FP oriented, like PureScript could be if you're working on the front end side of things, or Haskell or Scala. Otherwise, yeah, so I would not suggest as the best language to learn. On the other hand, it's a good language instead to, I think, spread FP concepts around the world, because it's also, because of course of its widespread usage in terms of actually developers working in TypeScript, which I don't know, compared to developers working in PureScript or Haskell around the world, are much, much more.
Nice, thanks. Let's see if any other question comes out. Okay, if not, let's thank Giovanni again for the nice introduction to TypeScript and functional programming, and with a virtual applause. And also let me remember that the next month, Matthias Verreis will talk about parser combinators. So if you want to stay updated with the next talks, you can find us on Twitter or on our website, functionalfest.com. So thank you all and see you next time.
Thank you. Bye.